Alright, so today we're going to talk a little bit about mutual inductance. And mutual inductance happens when you have two coils of wire where you're changing the current in one coil and inducing an EMF in a second unconnected coil by changing the magnetic flux through that coil. Remember that magnetic field caused by a coil of wires is related to the current in that coil of wires. If you change the current, you change the magnetic field, and so you can induce EMFs in other coils of wires that are close by. So changing the current in coil 1 changes the magnetic field that's produced by coil 1. Of course, that magnetic field is related to the number of turns of the coils of wire. That means the magnetic flux in coil 2 changes and induces an EMF in coil 2. That change in magnetic flux should also be related to the number of turns in coil 2. Now it's worth pointing out that di dt should be related to change in flux, and change in flux should be related back to E. This process is what's called mutual inductance, that you can have a change in current or EMF in one set of wires induce a current EMF in a second set of wires. So let's look at how this works. So we can define a term that we call mutual inductance, and basically what mutual inductance really does is it's a way of defining the inductance of this system based upon how does coil 2 interact with changes in coil 1. And so if we look at this, we'd have the number of turns of coil 2 times the flux through 2 caused by the magnetic field of 1, that's what I mean by the flux to 1, divided by the current in 1. And the reason why I put the current in 1 in here is that really the current of 1 is related to the magnetic field that's going through loop 2 or coil 2. So if we rearrange this formula here, M21 is really the mutual inductance of 2 with respect to 1. We end up with this relationship. Now if we wanted to figure out things about EMF, remember EMF is related to change in flux. So we could really say the EMF produced in coil 2 by changing fluxes in coil 1 is related to mutual inductance of 2 caused by 1 times, well, the change in current in 1. And that would be really your way of calculating the EMF produced in 2 caused by changes in coil 1. Now, it happens to work out if you did the same process, only changed EMF in coil 2 or changed current in coil 2 and looked at what happened in coil 1, you get a similar equation except all the 1s and 2s change. Now, what's interesting about this system is that the mutual inductance of 2 with respect to 1 and 1 with respect to 2 are the same. You can actually do some algebra and prove that that's true when you work it out, that you should get the same value, mainly because, well, the ratio of numbers of turns stays the same. The cross-sectional areas stay the same. The lengths stay the same. And so we can actually define this mutual inductance value, just M, and say that if you're changing current in 1, it induces an EMF in 2. If you're changing the current in 2, it induces an EMF in 1. And it's related to whatever this value of mutual inductance is. So let's test this out. Let's find the mutual inductance of a pair of coaxial solenoids with the same length L. Solenoid A has radius RA and NA turns of wire. Radius B is smaller with radius RB and NB turns of wire. And I'm going to pass a current IA through solenoid A, which is the bigger of the two solenoids. So we know the magnetic field caused by A should be mu naught IA NA divided by L. Well, what this means if we calculate the mutual inductance of B with respect to A, it should be number of B times the magnetic flux of B caused by A divided by IA. So if we wanted to calculate the magnetic flux of B, it should be the area of B times the magnetic field caused by A. And so if we actually work that all out, that's the value I end up with for that value for magnetic flux. Remember, this here is the magnetic field caused by a solenoid. This is the area or the cross-sectional area of wire B. So we plug it all in, we get, there you go, there's the magnetic field caused by, or the mutual inductance of B caused by A. We work it out. Oddly enough, the current cancels out in this case, and we really get NB NA mu naught pi RA squared divided by L. Now it's worth pointing out the same would be true for MAB. So the reason why the same would be true for MAB is if you did the exact same thing going backwards. You'd have mu naught IB NB over L as BA. MAB would be NA flux of AB divided by IB. Flux of AB would really be BB times, wait a second, AB, or excuse me, BA, or BB times AB. This should actually be an RB squared in here. Excuse me, I screwed that up, because here's an RB squared. The reason why the area should be the same is, well, the area of the magnetic, or the area in solenoid B that contains a magnetic field is really just, well, that inside area there. So you actually end up with the same relationship either way. And the cool thing about this is if you calculated the self-inductance of coil A and the self-inductance of coil B, you could actually combine the self-inductances of two coils to find the mutual inductance. That is the square root of the self-inductances multiplied by one another. Now, one place where we use mutual inductance all the time, even if you don't know it, is in what's called a transformer. Basically, in a transformer, what you have is a current with one voltage coming into the transformer, and you're causing a magnetic flux. And as you're changing that magnetic flux, you're inducing a current in a second set of wires. So let's look at how this works. So we know how these two voltages relate to one another. They relate to changes in flux inside of them. Voltage of the secondary, I'm going to call it S. The secondary should be number of loops in the secondary times change in flux of the secondary over change in time. And voltage in the primary should be number of loops in the primary times change in flux in the primary over change in time. It's worth pointing out the change in flux, the total change in flux should be the same for both of them. You have the same area in this case, the same magnetic field, and so all of that should be the same. So we should get this ratio here, that voltage in the secondary divided by number of coils in the secondary is equal to voltage in the primary times divided by number of coils in the primary. And so we get this ratio of voltage in the secondary to voltage in the primary is number in the secondary to number in the primary. So say you had a power line with 10,000 volts and you wanted to do what's called step down to, say, 100 volts. Well, you'd have a primary with something like 10,000 loops of wire and a secondary with 100 loops of wire. Now, it's worth pointing out that in that process, you also change the current. That as you step down the voltage, the current usually goes up in that process. So when you're talking about a transformer, basically what a transformer does is it takes high voltage and brings it down to low voltage through mutual inductance, or low voltage and bring it up to high voltage through mutual inductance. This happens in all sorts of places on our power grid. Usually what happens as you step down, so go from high voltage to low voltage, you also increase the current. The induced current is greater than what the original current was. Usually when you step up, going from low voltage to high voltage, you decrease the overall current in that process. So that's kind of a quick overview of mutual inductance and at least one application of mutual inductance. We'll start looking at in the next couple lessons are circuits containing inductors. We'll start with the RL circuit and then we'll move to the LC circuit and talk about how those circuits really act with one another.